So innovations in pavement type selection topics. The last little bit for the day. Stringless paving. There's not been a lot in my decade in the industry that has really revolutionized things as much as this is. It's changing the speed of construction. It's changing how the owners interact with the contractors. Because it used to be the case that the owners did everything behind the scenes and they would hand you a sheet of plans. The contractors had to decipher what that actually meant to then build things according to the designer's dream. Now, the owner does the design inside of a computer and then they give the contractor exactly what's going to be built. There's no more interpretation. It's more of a collaboration that's happening. ACPA has a webinar on this topic of stringless paving as well. Again, that's another one that's free. Gives you a lot of the good information on this. So this is an alternative to our conventional stringline paving. And we're using electronic guidance, things like GPS and lasers on site to replace the string lines. So this does all of the steering and elevation control, every piece of it. So sometimes we refer to this as 3D paving. There are a lot of benefits. It's much less labor intensive, reduces a lot of our prep time. The engineers that we have doing the surveying are harder and harder to find, so they cost more and more every year. This replaces them, not to make them redundant or obsolete, but there are still engineers and technicians necessary to work this equipment some. But the engineer's design goes directly into the machines. There's less points of error possible because exactly what I drew in my CAD file is exactly what gets built. I don't have someone interpreting into a string line what that is and then have opportunities for errors from that point and then on to the paving equipment. So all of that work that I showed you earlier about the surveying and the hammering in of reference hubs and setting up the string line, all of that is gone. Now, in conventional string lines, we have to have these straight chords or tangent sections as we go around curves. You can see that built into the side of the pavement. With stringless paving, it's perfectly smooth. It's the exact mathematical equation of that curve, both in the horizontal direction and vertically. So it's a much, much smoother end result. Extends beyond paving. We use it for earthwork. We use it for barriers. We use it for curb and gutters. So any piece of roadway construction equipment at this point, we can use stringless paving on. Two most commonly used types, we're using total stations, robotic total stations. That's this piece of equipment you keep seeing. It's basically just a digital eye. Or we can use GPS and laser control. It's slightly less accurate. We use the GPS for X and Y, where we are on the Earth, but GPS isn't particularly good at telling you your elevation, not to the tolerance that we need for roadway building. So we have to augment that with lasers on the ground if we take that specific approach. But the total stations is the most common. So on the piece of equipment, we have a computer and software to run all of that. And that's usually a small touchscreen panel placed right alongside the panel that the paving operator uses to control the vibrators and everything else. We have a dual access slope sensor, which is just this little white box. It's no different than what you have in your cell phone that tells it, I'm tilting my phone this way or that. Same technology, just attached to a paver. We have masts, which are just poles sticking up into the air, that on top of them have these 3D prisms. And then we have radios, which talk back and forth to the computer. So that's these little devices you see here, the 4 of those behind that touchscreen computer. Now in the field, we have our control points, those robotic total stations. And we have radios talking from that back to the paver. So there's this entire, basically, wireless internet system for these devices to talk to each other called CAN bus. And messages are just constantly being sent between the different components. We have our robotic total stations, which can sense where the paver is. That's all that they know. That's the eyeball pointing at the paver, telling it, I know where you are, which it radios that to the computer. The computer knows where it should be, because that's what has the model. There is some human intervention possible, but that computer controls what the paver does. And it talks back to the eyeballs to see if what it did was right or not, and if it needs to correct what it's doing. So here's that in more of a schematic approach. Just as with stringline setup, we start with those benchmarks, those places on the earth that we know exactly where it is. And those are usually developed by your local government. From there, we do have to use some surveying to control the exact location of our control points, which are just prisms. So we know exactly where that prism is in space. So our robotic total stations really do a lot of the work. That eyeball talks to the prisms, 3 of those, to triangulate its position. So it doesn't matter where you set up this total station. You have 3 reference hubs, 3 control points. You just bring this total station out, set it up, it rotates out around, and it can tell you exactly where it is. So we have a couple of those. Through the radios, it talks to the onboard stringless computer, the piece of equipment on the paver. That tells it where it should be, based on the 3D model. We've already input that directly from the owner. So we have the last component, those dual-axis slope sensors, telling us the X, Y, and Z of the paver. And in the end, the machine control adjusts. So how the paver is angled, how it's rotated, all these different directions that it can go through its hydraulic movements that were normally controlled by the string lines. It's all done now by that onboard computer. And it's interesting to see this in action. The contractors, when they first get introduced to it, are very hesitant that they can just not touch things and it will magically go where it needs to go, but it really does work. This is an illustration of the process. So we've got our slip-form paver. Our masts here have prisms on top. So that's how we figure out where it is in space. Our total stations, we have a couple of those around the slip-form paver, are referencing these control hubs, which we set using surveying. We have one total station telling us the as-built constructed thickness with a rover. So we have 2 total stations pointed at those masts. Constant feedback loop. So the paver knows where it's going. If it starts to go in the wrong way, the total stations will talk to it and say, fix what you're doing. The problem becomes that we have a limited range. It's about 100 meters. So once we get far enough away, we have to leapfrog, so change the control from one of the further away points to a new point. And as we're progressing constantly, that one operator, one person here, is continually moving the total stations forward and controlling the entire process. Just one person. So all of that labor that we had in stringline setup and everything else, now the model goes directly into the paver, and one individual moves around to make sure that the paver can talk to the model. So we got too far away from that one. The rover had to move the one that it was using for as-built thickness forward, go grab that one, and now bring it around. That's how paving continues. It's always referencing 3 points on the ground. Sorry, 2 points on the ground. Now, there's been a lot of practical components to getting everything correctly. The masts, for example, it was originally recommended to have one in the back and one in the front. But as we go into turns, we found that we got a lot more crossover issues, and having both of the masts at the back directly over what is being slip-formed gives us the best indication of exactly what we're building. Because otherwise we had to translate that distance to the front of the paver into the models. So that's a short introduction to stringless paving. It's really cool technology. It did not start in paving. It started in earthworks, and it's found its way into paving operations as the accuracy of it has improved over time. So some equipment advancements. We have progressed very quickly. In the initial days of roadway construction, early 1900s and before, we did not have trucks. We had to actually build rails to build roads. So we would build a railway. That allowed us to transport the materials to build the road, and then we'd build the road. Prior to that, you would see wagon wheels and a lot more labor-intensive methods, but to get production, we actually built railroads to build roads. Some things do still look familiar, though. These are some pretty early photographs. We have a bridge. We have someone applying curing compound. We have a different joint built into this here. That's probably a redwood expansion joint. We don't use those anymore, but things start to look familiar. Some of the recent advancements that we've had. Zero clearance paving. They're right up against that Jersey barrier. So the way that's accomplished is we have our 2 tracks on this side. There's no track in the back left. We have a track in front of the paving. And this back left corner is essentially cantilevered out so that we can pave right up against that barrier. Here's a photo from the front in the bottom right, where we're paving right up against this edge, and you can see the track has been moved to be in front of where we're depositing the concrete even. So we can make these adjustments based on clearance limitations. In this case, the entire paving kit. So we have the paver over here on the left, really, but the vibrators and the pan and everything else are just cantilevered out. We're now seeing variable width pavers. And what these allow us to do is reduce the time of adjustments of width. Traditionally, if you were to change the width of a piece of slip-forming paving equipment, it might be a day or 2 or even 3 to accomplish that. Because what happens is they have to adjust the entire width of the frame. It's a very rigid piece of equipment, so they would have to separate it, add in sections, and then pinch it all back together. Now we basically have telescoping frames. So as we're moving forward, if the pavement gets wider, the paver can just adjust for it. So it's a third dimension. We're not just placing uniform strips anymore. We can change the width on the fly. And only through 3D paving models has that really been a very smooth transition. To accomplish that with string lines, you have to have a string line on both sides, and the surveying becomes a little more complicated. So we're seeing these now from all the major paving manufacturers. Real-time smoothness. We saw the photo on the left before. This is a readout of what that looks like from the Gameco version. So in real time, they are seeing the International Roughness Index, the metric of smoothness that they're being held accountable for. So from the contractor's perspective, if the owner is not happy with how smooth the right is, all they have to do is give them the printout from that to say, this is what I built. If somehow there's more curvature of the slabs and it's rougher than you want it, maybe it was the materials or your specifications or something else that caused that to happen. But this is how smooth I built it. Now, you don't have dowel bars here, but you might still find this interesting. We have this device very similar to that magnetic imaging device for thickness estimation, but this we use to image dowel bars. So we place a plastic set of rails. There's no metal at all inside this rails. Even the screws are plastic. The person operating this device cannot have steel-toed shoes. You cannot have a truck parked near this. because it's that sensitive to any sort of metal near it. So we place these plastic rails and drag this suitcase-looking device over the top of the rails. And it gives us a readout of exactly where all of the dial bars are and how misaligned they are in every direction. So we can use this to see, in this case, the basket's separated and the dials have fallen like that. So we see the back ends that are affixed to the basket. In the case all the way on the right, it looks like the basket just got pushed and skewed. Now, we don't have widespread problems from dial bar misalignment. So this is a solution looking for a problem in many respects. Now, in the US, we found that all of the state agencies now all of a sudden are concerned with their dial bar misalignment, even though we've never had a problem. There's no tie between performance and dial misalignment. And there's been research into that. But we can now test it, so we are testing it all over the place. It's a relatively quick procedure, but it's very, very accurate. It only works on round dials, though, so far. The future of construction, just some of my personal opinions about where I think things will go. We'll probably see stringless GPS integration into joint layout and sawing operations. What I mean there is, I would imagine in the next 5 or 10 years, we will be able to go out into the field and using the same equipment that we use for stringless paving, identify exactly where the corners of a drainage inlet are, and exactly where the corners of a manhole are, and exactly where the edges of the pavement will be. And then feed that into a model in something like a BIM system, an integrated management system, and then have the joint layout just automatically take care of itself. Not only that, but then have the saws all be GPS guided, so the operator doesn't have to do anything other than bring the saw into the field and step back and watch it go and cut joints. I don't think we're as far away from that as you might imagine, but that will get rid of a lot of the question in the contracting element, because any contractor outfitted with the same equipment will build the exact same joint layout based on exactly what's in the field. This device in the top right does sawing and sealing in one piece of equipment. It will cut all your longitudinal joints and your transverse joints and do the sealing all in one piece of equipment. So right now that's a lot more people being put to work, but we're trying to automate things to that degree to get high production, especially on these thin overlays where we're paving very, very quickly. In the end, though, I really don't know what we're going to see. The manufacturers don't reveal new ideas until all the patents are filed and ready. I just, for the interest of comedy, have my favorite patent that I've ever come across. It is a dust cover for your dog. You can patent pretty much anything, and people do. So the economics of pavements, in the final stretch. Life cycle cost analysis, or LCCA. So there's 4 decision points from my perspective in pavement type selection. Historically, initial cost has been, that's it. That's the only decision point. Now we're having a dialogue about other things. In the modern era, we're talking about cost. That's still the biggest piece. We're talking about the user experience, so how smooth the ride is, if it's objectionable in any manner, if it's causing damage to people's vehicles as they pass. Safety of the ride is increasingly important. And lastly, and this is probably too big, I was joking about this during one of the breaks, sustainability. We keep talking about it, but no one is making decisions based on sustainability. I don't care where you are in the infrastructure space. It's part of the dialogue, it's part of the research, but no one's saying, yes, we absolutely did that because it was more sustainable than the other, even though it cost a lot more. It just is not happening. So sustainability is on our radar. but it's not really driving the decisions. Cost is still king. That's the number one decision point. Now, we are fortunate in that the discussion of life cycle cost has become more and more common. So a couple notes on things. Concrete has a lower inflation rate. Now, this is from the US. I don't know how true it translates to Chilean prices on things, but this is our producer price index for asphalt in the black line, and concrete in the green line. And the red line is consumer price index, CPI. Now, the consumer price index in the US is our metric of inflation. So from 1950s up to the 2010s, over that time, the dashed line you see is a 3.9% compound annual growth rate, CAGR. So 3.9% per year, about 4%. That's how much inflation has been in the US over that long of a period. That's the number you'll most commonly see referenced. Now, if you look, the concrete products producer price index has inflated at a rate even lower than that. If you were going to invest in anything, you would have been better investing in a broad index of inflation than in concrete in the United States. So cement producers aren't as well off as they might think from that particular perspective. But we see that, while there have been increases year over year and across time, there's not too much variability. There's not massive jumps in concrete prices. It's relatively stable. Asphalt prices, on the other hand, because of oil embargoes, supply and demand issues, and other challenges, have been much more volatile and increased at a much higher degree than concrete. In fact, over that time frame, we're looking at about 5.5% compound annual growth rate. That has changed in the US, the competition between concrete and asphalt, to a very large degree. Now, this is just pricing. There's a lot more to this challenge. In talking about this particular perspective of the marketplace in Zimbabwe 2 weeks ago, their challenge is worlds different than it probably is in Chile, and it definitely is in the US. There, they don't have hot mix asphalt. They get the emulsion asphalt that South Africa doesn't want. They have none of their own refineries, so everything that they pave with is imported, and it's of a very poor quality that gets them between 5 and 10 years max of performance. And they're paying about a 40% premium over what the exact same bitumen goes for in South Africa. So this isn't, I'm not trying to suggest that what's happening in the US is suggestive of the entire world and the example of the entire world. I'm asking you to locally have a discussion about these sort of factors because they are important. So the import-export practices and the refining process can have a huge impact on things. In the US, because of the price of the other materials, things like jet fuel and diesel fuel and gasoline, got to be so high, the refineries installed devices called cokers. What these cokers do is take the long hydrocarbon chain that is asphalt and break it into very small parts, which are diesel fuel and jet fuel and other higher yield, higher margin products for them as refiners. Now, it used to be the case that we would have enough asphalt to meet our demand after all of this other refining process. But the economics of the refining process themselves in many parts of the world have changed because of the price of the other components. And asphalt, while it used to be a byproduct, is very much a commodity. It's part of the pricing structure to maximize their margins as a refiner. And that's only happened very recently in history. And globally, we don't yet know the consequences of that anywhere, I don't think. But this is impacting things on a local level. Point being, in the US, because of the things that have happened in recent times, Concrete can now compete on initial cost alone. We don't even have to have the discussion we're about to have on life cycle costs. Because of these massive increase in asphalt prices in the last 5 and 10 years, for a comparable design, initial cost alone in many areas of the US, concrete can be lower than asphalt. And it's a service life that's twice as much. So here's the plot that I said we would get to. This is based on a survey of state agencies in the US, their expectation of how long their pavements will last. Asphalt is in blue. We have at least one state that says 1 to 5 years. That's all that they expect for their asphalt. Some are 6 to 10, 11 to 15, 16 to 20. The average is 13.6 years. For concrete, their expectations are quite a bit higher. On average, 29 years. Over twice as long is what they're expecting. And it costs just as much right now. So it's become very much a no-brainer as long as the state agency is willing to accept that the world around them has changed. But we still do talk about life cycle cost. This is a real-world example. It seems exaggerated, but it is not. This is from a local residential street in Wisconsin. And they had records of performance and costs for their concrete and asphalt pavements locally. And this is their real expense diagram where the height of the arrow is indicative of cost, and the point in time in which it occurs tells you when it happens. Now, this is an area where they had 100-year-old concrete pavements that had performed beautifully. They had no concern about building a new concrete section, say for $374,000. That will last 90 years with some maintenance and preservation along the way, but not too costly, mostly slab replacements, sealing, things like that. Their asphalt alternate was about, 20% cheaper in initial cost. And its maintenance wasn't any worse over 30 years. But it only lasts 30 years. And after 30 years, they had to reconstruct that section. And they had the same maintenance cycle, and they had to reconstruct it again. So over time, while the asphalt section was cheaper up front by 20%, it ended up costing them a lot more. So they went with concrete in this particular case. Wisconsin is one of those states that has, in some areas, very recently made this transition. The city of Milwaukee, for example, they were doing alternate bidding for about 3 years. And concrete won all of the projects on initial cost. So they no longer build asphalt pavements in the city of Milwaukee. Everything that is new is concrete because they've recognized the sections that they have lasted so long. Why should they build with an inferior product if it's going to cost them more? Now, failure to account for this is short-sighted. If we're looking at our pavement condition, and over time, and we start with great condition for either pavement type, and we have some minimum acceptable level, the concrete pavement will just take longer to get to that minimum acceptable level. We'll do some sort of preservation, and it will continue. The asphalt pavement just has a shorter cycle. They're working on extending that in many regards, but I don't know anyone that will argue that the cycle is longer. So if we look at the cumulative cost, well, the asphalt might be less costly in the beginning. As soon as we have one of these activities, an overlay or sealing of the surface or sealing of cracks, it costs us money. And those costs add up over time. And that's all that life cycle cost analysis is trying to track and predict to help us make better decisions up front. Here's a real-world example from the Louisiana Department of Transportation. And they wanted to track what the impact on their decision-making was based on considering of life cycle cost analysis. What they did was looked at actual bids based on the daily traffic of the roadway. The initial construction costs were such that it took about 35 or 40,000 vehicles per day before the concrete and asphalt alternates were even, were similar to each other. Before that, so any lower traffic, and the initial cost of the asphalt would be less than that of the concrete. Now, when they looked at the life cycle cost, they found that break-even point to be closer to 10,000 vehicles per day. And this was before that massive spike in asphalt prices that they did that study. The break-even point has to be further to the left there at this point in time. Now, I'm not suggesting that if you're not comfortable with concrete pavements, you do everything in concrete pavements. I'm suggesting is that this idea, this approach of alternate bidding is the only way by which we can account for things and start to consider these particular details, and more importantly, to bring competition to the market. So most of those images you just saw are available in this life cycle cost analysis guide that ICH translated last year. So talk to Mauricio, that's readily available. I think that ACPA is intending to distribute that through FISM very soon as well. So what this competition idea boils down to is that it's in the best interest of the owners, and the taxpayers especially, to consider these sort of competitive approaches to bidding. Now, there is a very complex relationship. There's been a lot of research in this area about the number of bidders, the volume of the market, the unit price, all these sort of factors that are all changing at once. But if you look at this plot here, we see our unit price. Asphalt is the blue dots, light blue, sorry, in dollars per ton. Concrete is the purple squares in dollars per square yard. And the x-axis is share of pavement spending on concrete. So these are state agency results, real bid prices in the US. And we don't have any state that builds more concrete than asphalt right now. We have some that have more concrete on the ground in their jurisdiction, but we don't have any that are paving more concrete than asphalt. But the trend is such that the larger the share that is concrete, so the more competition, the more consideration of the alternate, the lower the unit prices. So there's a clear trend there between lower prices for both paving materials with increased competition. There's been a lot of reports and studies recently. The larger the number of bidders that you can attract, whether it's within one material or alternate materials, the lower the prices. All these sort of things put pressure on competition. They also reduce the variability in the unit prices as well. So through this consideration of competition, alternate bidding, and just considering both pavement types on any given project, the owners can end up paving more. The unit price drops down. They can either pave a larger contract with that same amount of money, or if they choose to work on other contracts as well. But anything that they can do to reduce their costs will help them do more with the budgets that they have. Now, there's an alliance in the US for pavement competition, which has a lot more information on this. If you do want that URL or the slides themselves, that's the website that has a document that discusses this particular aspect of competition in the marketplace. I think the last note that I have is on sustainability, and then we're done. And while life cycle cost analysis is something very reliable, you might not like the process, you might not like the results or the numbers, but it's something that as engineers, it's founded in economic principles. We can't argue with the process. It's absolutely fact, the results that we get. Life cycle assessment, it's a little bit cloudier. Now, everyone always wants to know what's the more sustainable pavement type. I'm here to tell you the honest answer, neither. It depends. It always depends. Cement can be much more CO2 intensive to manufacture than asphalt can be to extract and refine. It depends on who the refiner is, the haul distance from extraction, and a lot of other factors. So the bitumen itself versus cement, cement is probably more CO2 intensive to manufacture. We only use so much of each binder in either pavement type. So then it matters about how much the percent of the section is that is binder, how thick the section is, the haul distance from where the bitumen was imported or manufactured, same with cement, extraction and transport of raw materials. So many variables at play that there's not one single answer about which is most sustainable. We do have methods, standardized methods now, to quantify the CO2 emissions and the environmental impact. But the professionals working inside of that particular aspect of things, that space, if they're telling you the truth, they should be telling you it's very project specific. If you'd like to see some case studies, we can provide you with those, but they go one way or the other. It all depends on the particular circumstances of the project. So the materials used, recycled content, byproduct usage, so things like slag cement and fly ash. If there are byproducts, they will help. The use phase is probably the most contested at this point. In the US, the Massachusetts Institute of Technology, MIT, is doing a lot of work in that particular aspect of things. Everything from the surface color of the pavement to its rigidity can impact the use phase. Now, the surface color, that's actually something that we can show a difference on now. Minnesota DOT has standards that allow for either a further light spacing or a lower wattage bulb when concrete is the surface, because it's lighter and has a higher reflective property. So we can use less energy now if we build with concrete and account for that in the lighting design. The challenge is you never know if you're going to overlay something with asphalt. So the designers like to just use the same light pole spacing and the same lighting design that they would use for asphalt up front, and then the concrete is just very, very bright whenever you have to go walk or drive on it. But the reality is that that benefit exists if someone chooses to leverage it. The rigidity of the surface, studies from Sweden to Texas to now MIT have shown a small benefit to concrete versus asphalt. With asphalt being flexible, the way to think about it is on a very, very small scale, you're always kind of driving uphill. Unless the asphalt is very, very cold, such that its modulus approaches that of concrete, so you're somewhere like Alaska, it's always a little bit flexible, which means your car is going to sink in just a little bit, and you're always trying to ride out of that. With concrete being more rigid, that's not the case. So they all show a small, we're talking 1, 2, 3, up to about 5% reduction in fuel usage on concrete relative to asphalt. But in any of these topics, the industries are just butting heads. I don't know that there's any clear answer. It is very project specific. Another one of the CP Tech Center's documents is on sustainable concrete pavements, a manual of practice. That's not intended to compare asphalt to concrete very much. It's more there to provide guidance on how to build and design more sustainable concrete pavements, to raise our own bar rather than comparing things, to make our product better. But no general answer. With that, are there any questions on innovations, LCCA, LCA, any of these other topics?
¿Alguna pregunta? ¿Alguien tiene algún interrogante? ¿Cualquiera de los últimos módulos?
Now, there were about 15 slides we didn't get to on rehabilitation. I would assume everyone would like to go home rather than sit through more slides. So if you do want to download the slides, you can review those and send any questions you might have to Mauricio or myself.